Okay, so welcome everyone. Good evening, good morning, good afternoon from wherever you are. And uh, Today we have the 21st invited talk in the series for complex systems and dynamics. And today we have with us Dr. Arnaud Dragicevic, who has a very interesting uh, topic today to discuss stochastic control of ecological networks. So, Dr. Arnaud is a senior researcher in bioeconomics at INRAE, which is the French National Research Institute for Agriculture, Food and Environment. He holds a PhD degree from École Polytechnique, Paris, and a DSc degree or habilitation from the I. Marshall School of Economics, AMU. Sorry about my French pronunciation. So his research interests include bioeconomics, socio-ecological systems, and sustainability. The modeling tools he holds in high regard are the graph and game theoretic settings seen as governed by evolutionary dynamics. So over to you, Dr. Arno.
Okay, well, first of all, thank you very much for giving me the opportunity to present this ongoing work. Thank you, Cyan, for organizing the seminar. So as has just been said, I'm Arnaud Dragicevic, and I did the following job with Angela Gurtu, who is a professor in management studies at Indian Institute of Science. I'm an economist but interested in complex systems. So any feedback from people specializing in mathematics, physics, and complex systems are welcomed. So I will now download my presentation. Do you see it well?
Yeah.
Okay. So the, the title of my talk is Stochastic Control of Ecological Networks. As I said earlier, this is a joint work with Angela Gurtu. So let me first present the context. Land use changes have led to the ecological fragmentation of territories and habitats, which provoked the erosion of the biodiversity and the intensification of pressures over the natural environment. Now, the European public policies have emphasized the need to ensure interconnectivity through the establishment of ecological networks between natural reserves. As an example, the French Environment Roundtable Act has been voted, and it stresses that the protection of biodiversity and ecosystems in general should be undertaken by means of greenbelt networks. In practical terms, this takes the form of supplying biodiversity hotspots and forest green corridors. Now, those are meant to facilitate the adaptation of vulnerable species to environmental disturbances. However, the implementation of ecological networks in forest ecosystems must not prevent the foresters from exploiting the timber stands. For the multifunctionality of forests is about both providing wood products as it is about protecting the ecosystem services. The control devices put in service to provide an ecological network are restrictions in cuts to parts of the forest, the establishment of a number of dead trees with the aim to create senescence isolates, or the performance of forestry work undertaken to ensure some optimal forest cover in the woods. Now, the question that we are interested in is as follows. What does it take to preserve the connectivity of an engineered ecological network in uncertainty? Now, the topic of connectivity preservation, once the network has been put in place, has been rather neglected in the literature. Most of it proposes a framework where the nodes chose to form or maintain links at a certain cost. And contrary to the existing papers, which model a budget-constrained optimization in the design of optimal corridors, we turn toward a connectivity-constrained optimizations. Now, corridors have to be implemented by taking the precaution of verifying that their number and sizes are functional. And rather than the maximization of discounted expected payoffs of social planners, what heightens our curiosity is the capacity of forest managers to provide a stable ecological network, what is more in uncertainty. Whereas the studies, such as the one, for example, of Schneider and colleagues, consider the opportunity costs to optimize the spatial distribution of conservation measures, we wish to size the financial resources needed to preserve the network connectivity over long periods. As a matter of fact, increasing uncertainty puts it at greater risk of rollback. Now, the aim of the following work is to model the maintenance of ecological networks in forest environments built from bioreserves, patches, and corridors, when these grids are subject to random processes such as extreme natural events. The management plan consists in providing both temporary and sustainable habitats to migratory species. It also aims at ensuring connectivity between the natural areas without interruption. After presenting the random graph-theoretic framework, we applied the stochastic optimal control to the graph dynamics. Our results show that the preservation of the network architecture cannot be achieved under stochastic control over the entire duration. It can only be accomplished at the cost of sacrificing the links between the patches by increasing usage of the control devices. This would have a negative effect on the species migration by causing congestion among the channels left at their disposal. The optimal scenario in which the shadow price is at its lowest and all connections are well preserved occurs at half of the course, be the only optimal stopping moment found on the stochastic optimal trajectories. Therefore, the optimal forestry policy has to cut down the timing of the practices devoted to the biodiversity protection by half. Let me now present the model. Now consider an ecological network built from ecological areas and corridors. The grid is based on the Euclidean metric defined on dimension R. The link formation of forest managers is contingent on engineered distances between the network constituents. Their purpose is to enable living species to migrate from an area to another. The species are allowed to move in all directions, such that the network is an undirected graph gamma. The graph consists of vertices capital V, where I and J give indication of two randomly chosen areas. Nodes can either be intermediary patches or bioreserves, the second being the targeted areas in which the migration ends. So in ecological networks, target nodes represent the bioreserves, the aim of which is to accommodate the species in the process of migration. Unmarked nodes stand for the patches which temporarily host the species heading toward bioreserves. So in short, consider the set of edges capital E composed of n-dimensional vectors at time t. Let capital X be the vector of n edges between patches at time t. Likewise, let capital Y be the vector of n edges between bioreserves and patches. We consider that both the edges and the graph vary in finite time for t within 0 and capital T. Now consider capital A to be an adjacency matrix with non-negative elements Aij, and assume that Ij belonging to capital E, implying that two nodes separated by a proper distance are purposely connected if and only if Iaj is positive. Finally, assume the existence of a convex hull of vertices omega at initial time step 0 as an n-simplex with the Euclidean norm in R. The convex hull is a mathematical notation for both the existence and the maintenance of the structural network architecture. Now, in this figure, you can see a simplified illustration of a forest environment formed of 5 vertices and of 6 edges. The ecological network built within the forest connects nodes I, J, and K, and O at time 0. Node O represents the final destination, that is, a bioreserve that migratory species are supposed to reach through patches I, J, and K. The graph is composed of patch-patch connections, such as XIK, and of one bioreserve patch connection, XJO. Now, since the distance between Ln I and Ln J are too long, it can be noticed that from the beginning, forest managers exclude both area L and its connections from the start, from the grid. Indeed, migratory species have a limited capacity of displacement, which cuts some nodes from the system of connections. Now, a successful forest management plan is to keep the identical topological configuration at both the starting time 0 and final time capital T, such that the convex hull at 0 is equivalent to the expected convex hull at capital T. Now, by reason of the stochastic processes governing natural events, the implementation of green corridors on random graphs is more suitable. We found ourselves in presence of a random graph capital J. It is defined with respect to the probability measure rho. The dynamic graph then evolves into a graph-valued random variable. In this second figure, one can observe that the initial convex hull is not equivalent to the expected convex hull at capital T. In that case, the randomized convex hull only includes nodes I and K. Because in expectation, XJO is no longer operational, and bioreserve O is deleted from the ecological network, the updated grid is considered to be disintegrated. This is not what forest managers want. They want to keep the initial engineered ecological network in time as it was initially. Now, deleterious stochastic processes can be tackled through stochastic differential equations. Continuous dynamics of the vectors of edges d capital X and d capital Y, which belong to domain capital D, are considered to obey the stochastic differential equations. They are in the following form, as shown by system 1. So the respective equations describe the probability distributions for the distances between bioreserves and patches, and between patches, to be at a given level at a given time. Now, while X represents an n-dimensional vector subjected to time-evolving stochastic processes, capital W reflects the local Brownian motion as an n-dimensional linear continuous time stochastic process. Brownian motion makes it possible to compute the probability of change in any direction during a certain time interval. As for vector B, it typifies a diffusion process with local drift. It means that it exemplifies the change in distance, initially meant to ensure the migration of species, between two nodes. The control vector ux, which belongs to the domain U, provides information on the use of the silvicultural control devices to preserve the ecological network. The first term is thus defined as the benefits at period t of controlling distances capital X at rate ux. On the side of the ultimate objectives, B represents the management policy of facilitating migration to bioreserves, whatever the initial vertex the population of migratory species find itself in. The local volatility, or standard deviation rate, is represented by its diffusion tensor profile through positive definite matrix capital L. The diffusion is the variance in the rate of change in a unit interval. It means that diffusion gives indication on the dispersion of the probability distribution. Now, volatility generates fluctuations in distances, which causes the use of control devices to fluctuate just as much. What the stochastic differential equation tells us is that in a small time interval, the variations in capital X are an amount distributed with expectation B and variance capital L. Now, to produce the control law, the application of collaborative devices to the task of all types of edges assembling necessitates to exert the joint torque control. Indeed, the dynamics makes it the overall control hard to implement, so that a joint control controller with dynamic responses is necessary. The differentiated connections between the patches and between bioreserves and patches are hence converted through dynamic control vectors to a single resultant joint control torque vector. The torque being additive, it represents a net joint control where the devices sum up for t between 0 and capital T into a common vector uz. We observe the following expression, d capital X, d capital Y, where ux and uy are now replaced by uz. We thus have to estimate the torque distribution as follows. The probability density function of random distances capital X and capital Y, that is rho z, progresses according to the parabolic partial differential Fokker-Planck equation of order 2. Now, the use of this equation enables us to study the Brownian motion when the initial probability distributions are unknown. The time evolution of the probability density function under control devices is apprehended through the following time derivative. The second part of the equation takes the form of differential operator f. Its goal is to obtain, by revising the rates of control, the average property of motion. We shall now consider the behavior of the system. So it is assumed that the system can be controlled, which means that the system is equipped with controllers, the position of which dictates its future evolution. These controllers are characterized by points uz, namely the control variables. Stochastic optimal control minimizes the cost of control along the entire time path. Its purpose is to preserve the ecological network at the lowest possible cost. Preserving the ecological network means that all random edges allowing for species migration remain intact throughout time. So by starting with the terminal time step and by ending with the initial one, we solve the optimization program backwards in time. The following performance function J ensues. Now the expected final cost is situated in the first term. Its form is an inner product that considers weighting function phi. The latter incarnates the distribution of shadow prices for achieving desired migration through stochastic joint optimal control UZ. The inner product is discounted at constant rate at time capital T. The second term of the performance function collects all expected costs discounted at rate R under control UZ. Integrating over time permits obtaining the present value of a continuous flow of costs. Now the performance function, the dependence of which comes from exponential discounting, is a two-dimensional convection diffusion equation. Just a second, because I have a black screen. I apologize for that. I don't know what happened. Okay, here we are back. Now the optimal control problem becomes the minimization of the performance function with respect to the cost of control, subject to the dynamics of joint distances. Put differently, we have to minimize J regarding UZ, subject to the following dynamics. Now, the solution to the problem consists in finding an open loop control sequence UZ, the latter being dependent on the cost recorded in the final state and on the costs integrated over finite time that reaches minimal cost of control. Now, the optimal control is also a penalty to any deviation from this level of cost. The necessary condition for desired controllability is that UZ star minimizes the Hamiltonian for T within 0 and capital T. We have the following Hamiltonian expression. Now, through the solutions of partial differential equations, the Hamiltonian covers integral terms. Probability density function rho is displayed in the first system. The joint distribution evolution in F prime, with F prime being the adjoint operator of capital F, satisfies the Green's identity. In other words, the linear operator equivalently acts on the boundary of domain D. The region under the differential operator is bounded, and the convex hull is preserved from growing infinitely. As for pi, it represents in form of a Lagrange multiplier the optimal control co-state or the shadow price. Now the Hamiltonian can be solved through the standard first order optimality condition by computing the partial derivative of capital H with respect to UZ. To put it another way, we have the following derivative. Now, the minimized Hamiltonian is convex both in capital X and capital Y. The necessary and sufficient condition for the minimization of the Hamiltonian is met. Such a property comes from the Arrow-Mangasarian condition, which shows that if in presence of continuous first partial derivatives with respect to UZ, capital H is continuous and convex is UZ, the Hamiltonian is minimized. Control sequence UZ is denoted as a global minimizer of the functional. Now, because rho cannot be identified, the inner product shall be computed by means of the derivative of the joint distribution. As a consequence of the Kolmogorov backward equation applied to continuous time Markov processes, the Feynman-Catch formula can be borrowed. The dynamics becomes as following. We have the following time derivative. Now the negative sign, I apologize, discloses the willingness to pay to ensuring connectivity of the ecological grid. The differential operator is bounded by the equality such that pi is equal to phi, where phi is the terminal condition at terminal time step capital T. Now, provided that rho generates from the linearity of the inner product the expected value of phi, the optimal control yields the expected joint distribution of shadow prices. As a result, we have the following optimal level of pi star. We know also that the optimization problem has to be well defined. In parallel, the integral has to converge. So we are now in attendance of a transversality condition, such the initial cost, the limit of the initial cost when t tends to capital T is equal to 0. In summary, pi star is equal to phi whenever t tends to capital T. Now, the result which we find here reveals the presence of real option valuation, in which an optional investment on natural resources, dependent on the costs to be incurred for the resource preservation, takes place. Real options are to be seen as the willingness of forest owners or managers, but not the obligation to undertake at a certain cost the stabilization of the ecological network, the state of which is governed by random processes for an additional unit of time. We finally have to decompose the joint torque by projecting the control onto the kate weight. Now, in an unavoidable fixed budget constraint driven by costs of control from 10, the control of the kate parameter adaptation is designed as follows, where KUZ between 0 and 1 represents the weight assigned to an isolated control, the remainder being given to other joints under scrutiny. Our last objective is to derive results in the context of a dynamic programming problem on the optimal stopping moment. Now, after having found through the formulation of an adjoint problem an admissible control device leading to an optimal trajectory of the graph, we aim at revealing the optimal stopping times. We are doing this because theoretical optimal trajectories can sometimes be desynchronized from the real context forest management. And this is particularly true in that forestry is practiced with respect to very long management plans. For example, the rotation in forestry, going from planting to harvesting, can reach a length of action up to 100 years. This approach, and I apologize, involves breaking the problem into a sequence of small moment decisions. We thus denote tau within 0 and capital T, the collection of stopping moments. We then define a sequence of value functions, capital V. It incarnates the implementation of the optimal policy throughout the sequence. The optimal stopping problem is defined as the following criterion, where we obtain the minimum of the performance function J at time T with respect to the upper level of the value function at time tau star. Now, provided that uz tau is equal to uz t, stopping time tau becomes an optimal rule. Now, looking at it more closely, it appears that the solution to the last stopping moment has already been formulated through the Feynman-Catch type equation. That is the time derivative of pi with respect to tau. Now, the risk of ecological network dismantling is minimized, which we summarize in the following proposition. The preservation of the ecological network architecture in uncertainty is undertaken under stochastic control through stochastic shadow pricing. The latter permits safeguarding the configuration of the network connectivity. In that case, the adjoint-based optimization becomes the time-evolving willingness to control. Ultimately, the adjoint variable distribution unveils, along the optimal timing sequence, the stochastic value of the network connectivity. I'm going to now talk about the simulations. So we are interested in the levels of shadow prices unveiled to ensure the connectivity of an engineered ecological network for an additional unit of time. Now, the processes under control are reduced to capital X equal to X1 and capital Y equal to Y1, with X1 and Y1 being two corridors subject to random variations. The non-linear dynamics match with their evolution in uncertainty. Now, the time evolution of distances between the patches, dx1, is a function of time, the distances between bioreserves and patches, and of the inverse cumulative distribution of the standard normal distribution. Equally, the time evolution of distances between bioreserves and patches is a function of time, the distance between the patches, and the inverse cumulative distribution of the normal distribution. Now, the fact that both types of evolution depend on complementary distances reveals that the migration objective depends on the sum of both types of edges. This property provides evidence for the cascade effects in natural environments, whereby a change is proportional to the node's number of interactions. In the supplied version of stochastic differential equations, we emphasize the fact that the ecological network needs to be connected despite the random occurrence of natural hazards. The dynamics under the joint stochastic optimal control are as follows, where kx1 and 1 minus kx1 within 0, 1 with ky1 equal to 1 by kx1 represent differentiated weighting of the torque once decomposed. Let's now take a look at the results from the simulations. Now, this figure depicts the dynamics of distances under stochastic optimal control operated in 5 simulation models with respect to different levels of k, going from 0 to 1, between the patches. All models considered, the average starting distance is of 12.67 at t equal to 0.01, and it reaches the terminal value of 4.87 at t equal 1. This corresponds to an average decrease of 3.61. The standard deviation, shown by the gray curves, tends to shorten until the optimal stopping coordinates, which are at t equal to 0.57. In detail, we see that after a sharp swinging of the distance up to 0.25, the mean edge stabilizes until reaching at the optimal stopping time the change value of 0.02. Beyond this time step, the distances between the patches are clearly on the rise. Now, this should be seen as a failure of the optimal control beyond the optimal stopping time. The success of control over the whole length is to be considered as relative. The safeguard of a set of patches shall have a limited effect on the species migration. And we can assume that the congestion among the least onerous channels is to be envisioned thereof. The next figure illustrates the dynamics under stochastic optimal control operated in 5 simulation models of distances between bioreserves and patches. Now, when all models are taken into account, the average value commences at 13.93 at t equal to 0.01 and closes at the final value of 4.87 at t equal 1. The average fall is of 12. Now, after sharp initial variations, it stabilizes after 0.43. It can be mentioned that once again, the optimal stopping moment is observed at t equal to 57. So the stochastic optimal control enables to maintain the configuration of the connections between bioreserves and patches until the optimal stopping time. For longer periods, the distance is clearly increasing. Nevertheless, the fall in the cost of control is much greater than in the previous case. Therefore, it must be highlighted that the control devices have a greater effect on the preservation of connections between bioreserves and patches than on that between the patches. The last figure represents the optimal path of shadow prices calculated from 5 simulation models dedicated to the preservation of connectivity of the ecological network against random processes. Now, the average value is of 46.73 at t equals 0.01 until attaining the value of 32.62 at t equal 1. Regarding the average fall, it amounts to 14.37. Now, after an interval of stabilization until the optimal stopping time t equals 57, where pi star is equal to 32.02, the standard deviation tends to enlarge. It goes from 13.23 at 0.57 to 22.81 at t equal 1. Now, contrary to what is expected, the optimal path is not in steady decrease along the timeline. As you can see, there is a decrease until the optimal stopping time. So after going beyond the half of the management plan length, this results in observing an increasing cost of control. We summarize these observations in the following statement. The preservation of the ecological network architecture in uncertainty cannot be achieved under stochastic control over the entire duration of the forest management plan. It can only be accomplished at the cost of sacrificing the links between the patches by increasing the usage of the control devices. The optimal scenario in which the willingness to pay is the lowest and all connections are well preserved occurs at the optimal stopping moment, be it at a half of the course. The optimal forestry thus has to shorten the timing of the practices devoted to the biodiversity protection by half. Finally, I'm going to give a couple of concluding comments. So this work aimed at providing a formal framework for the evaluation of financial resources needed to preserve the connectivity of an ecological network in uncertainty. Through the consideration of stochastic optimal control, we have been able to study the controllability of a random graph. By focusing on the optimal stopping moments, we have also shown that the optimal control of ecological networks is out of sync with forest management plans. Now, this means that we have been able to contribute to the literature linking biodiversity with rotation length. In that our results point out that the management of forests and the management of ecological networks within those forests are not subject to the same temporality. The inclusion of economic aspects of the biodiversity conservation makes it not possible to align the management of green corridors with the forest management plans. Indeed, the optimality, I apologize, the optimality of the shorter duration of endeavors dedicated to the safeguard of ecological corridors implies that the economic resilience and the ecological resilience do not obey the same matrix. Now, in that, our modeling framework gives indication on what a resilient network would look like. In detail, our findings go along with the discovery that biologically based rotations are typically 2 to 3 times longer than economic rotations for the same tree species and site conditions. Now, the policy implications of our work suggest that the duration of the forest management plan should be divided into 2 equal intervals. The revenues from the timber sales obtained at the end of the first interval would be invested in the preservation of the ecological network to its completion. Now, our work permits to develop an awareness on the fact that ecological sustainability depends heavily on the economic constraints, and the management objectives turn out to be a part of a large decision-making process that needs to be inclusive of a variety of parameters. Thank you very much for your attention.
So thank you very much, Dr. Dragicevic, for a very interesting talk. And would you like to take some questions now?
Yeah, of course. If there are any questions, I'd be happy to answer them.
Yes. So any questions? If the audience, can you please raise your hand if you have any questions? Okay, while the audience is, while we wait for questions, I have one question for you. What you have actually done is, instead of a budget constrained optimization, you have focused on connectivity constrained optimization.
Exactly.
Right. So essentially, the idea is that all the channels for migration, they should remain intact.
Exactly.
Yeah. So how does the usually, I mean, as you rightly mentioned, that most studies in the literature focus on a budget constrained optimization. So is this connectivity constrained optimization, is it much more expensive than the usual budget constrained optimization, or how does it work? How do they compare?
It's a very good question. Well, it depends. It depends on your initial budget. If you're doing a budget optimization, a budget constraint optimization, you might want to deliver a very small engineered ecological network. But you're going to fulfill your purpose, your objectives, because you're going to align your costs within the budget that you dispose of. Whereas if you're doing it from the ecological point of view, you know what for sure is needed for species to be able to migrate, and then you're trying to minimize the cost. And of course, it can be much more expensive than what you would have done if you only first considered a budget and then built an ecological network from it. But on the other side, you're still trying to minimize the cost. And this is something that is economically relevant.
Right. But in terms of practical implementation, I mean, most management entities would be working within a budget. I mean, if the required budget is much more, they can only put pressure on the policymakers. That's all. I mean, am I correct in my understanding?
You're absolutely correct.
Okay.
But we are trying to be as multidisciplinary as possible.
Right.
Saying we are not going to act as usual as economists. We're going to see what the ecologists and forest managers need or find as necessary. And then we're going to try to be as optimizing as possible.
Right. I have a few more questions, but I'll wait for if others have any other question. Anyone? Any questions? Yes, Shubhimal, please go ahead.
Thank you for a nice presentation. So I have a question which is not, I mean, it's more related to ecological network, but may not be directly related to your work, but maybe some sort of a solution if we can get. So let's say if you're talking about an ecological network where multiple components are, they are kind of connected with each other. And let's say when there is a stress, because we are essentially talking about anthropogenic stress or climate stress or any kind of stress, and these systems are, they get perturbed. And because of this perturbation, there are changes which happen. So links become kind of very dynamic, like some of the new links are getting generated and some of the links gets broken and so on. So normally Shepard and others, they normally hypothesize that, when there is a stress initially, there will be more number of links being generated to resist the stress, and after that it will fail, means then it will go from one state to another, which is essentially crossing the tipping point. So and again, very recently 2021 Schaefer has come up with a very new science paper where they have said that mean exit time is sort of a correct measure of resilience of any system, and in any network based system or ecological network and so on. So I'm just wondering that is there any way in the optimization, if we can really increase the exit time or the time of stay in the basin, so that we can avoid the tipping points in some way, if we can really think of a management practice. Something like that. I'm not very sure if I'm clear to my question, but is it something
well, once
possible?
again, thank you very much for your comment and your question. So if I understood well, and given my own knowledge, I can eventually say with respect to you, what you have said, that it can be resumed to the study of the convex hull.
Yes.
In that case, we can envisage two cases, low resilience or strong resilience.
Yes.
Now, in that case, my work and that of my colleague would be that of strong resilience, because not only do you endure a shock, but you go back to the initial configuration.
Okay.
Weak resilience would be to maintain the convex hull intact, such that you still have the same number of patches, bioreserves, and connections, but they might change because of this configuration. In that case, you're no longer trying to obtain omega 0 equivalent to omega at capital T. And this would be weak resilience, because you're only interested in the population of what composes the ecological network.
Okay. Okay, thank you.
As a follow-up to this, what you just now mentioned and what Shubhimal mentioned. So often here you are making the assumption that the existing links are the most optimal links for the population. I mean, that's an assumption that we are making, based on which we are putting the constraint that we want to maintain those links. But often we see that due to certain perturbations, new links that get formed, they might actually be more optimal in some sense. I mean, what are your comments regarding this?
I have one question before answering to your question. Is someone engineering the connections, or a node decides to connect to another node?
It's just, I would say that due to a natural hazard or something that has happened, there might be new connections that are being generated.
Okay, so let us assume that this is not a social planner who engineers a network. This is something that kind of occurs by nature.
Right.
So I see no difference in the optimality. I mean, if the new connection appeared, given the perturbation, maybe it's more adapted to the environment. So maybe its presence is more significant and necessary than the old connections. This is the only thing that comes to my mind like that without giving it more thought than that. But yes, it's a very interesting question, and this is something that can be eventually studied within a research project.
Right. So, any other question from the audience? I have one last question. You talk about this control devices that you want to put in. So, from a practical point of view, what could be this control devices that you are talking about? For example, in the case of you have a bioecological network, and then there is a hazard, and physically what do these control devices mean?
Yes, I talked about it in my second slide. The control devices are restrictions in cuts to part of the forest. So you're not cutting trees so as to enable species to be hosted and then to continue their migration. The establishment of a number of dead trees, which are not going to be used and sold as timber. To create senescence isolates. So many species like to accommodate themselves within those trees, or some performance of forestry work, some cleaning between the trees to ensure some optimal forest cover in the woods with those corridors.
Okay. And what are the time scales that you are working on all these things, on all these equations that you talk about? What is the time scale of the unit of time that you are considering?
That's a very good question. It depends on the type of forest. If you have a forest that you plan to manage for 100 years, then the optimal stopping moment will be 50 years. After that, you can no longer rely on the initial corridors that you have settled. If you have a management plan of 40 years, it means that the bioreserve preservation policy would last only 20 years. And you need to optimize it again after 20 years.
Okay. Thank you.
Thank you.
So, any more questions from the audience? Okay, I think there are no more questions. So then I would like to take this opportunity to once again thank Arnaud for this really wonderful talk. And it's a new area for me, so it was really exciting for me to listen to your talk. And thank you very much for offering to give a talk in our complex systems and dynamics. And hopefully someday we will be able to invite you here physically to our campus, and and we can have more discussions. So with that, I would like to thank you very much, and good evening to all the audience, all the participants in today's meeting. Thank you very much.
Thank you. Thank you very much. Thank you. It was a pleasure. Bye.
Yeah, bye. Good night. Thank you.